Okay, so thank you for the presentation. So I am a PhD student, and my name is Patrick Lare, and I'm working with Sylvie Pommier at Paris-Saclay Mechanics Lab, so LMTS. And the thesis is also founded by Safran Aircraft Engines. And today I will talk about non-local crack initiation criteria and lifetime prediction in fretting fatigue under variable normal loading conditions. Okay, so for the presentation of today, so I will first talk about the industrial context, and then I will explain what is the non-local approach, and then before concluding, I will talk about the lifetime prediction under variable normal loading conditions. Okay. Okay, so I am working on the lifetime predictions of contact zones. So for instance, the blade disc root attachment contact zone, which is subjected to fretting fatigue. So during the rotation of the machine, so and due to the centrifugal force, the blade came into contact with the disc. So we have let's say a normal contact with normal load P, and due to the fluid structure interaction between the air and the blade, so we have a microslip that appear at the contact interface, and this microslip can initiate cracks, and those cracks can propagate if we have fatigue force. So there is a need of a robust and predictive model to characterize the crack initiation risk in this kind of contact. Yeah. So one of the particularity in fretting fatigue is the gradient effect. And so we can see that on this figure, the crack initiation boundary depend on the gradient effect. That depends on the geometry. But to predict in a geometry independent way the crack initiation boundary, so a non-local approach was proposed by Montebello in his thesis, and we can see that with non-local quantities, so we are able to predict in a unique curve the crack initiation boundary. So this means that the non-local quantities take into account the gradient effect. So after the thesis of Claudio Montebello, so Guilhem also continue the works of Claudio, and he proposed crack initiation criteria to predict the lifetime. And after the thesis of Guilhem, so there is my thesis, and in the first part of my thesis, we extend the non-local approach to the similar azeotropic contacting bodies. And thanks also to the non-intrusive nature of the non-local approach, it can be applied to any displacement field. And in my thesis, we apply it to, for example, to the AC displacement field. Okay, so I will move to the second section, so the non-local approach. Okay, so I will first defining what is fretting and fretting fatigue. So we have fretting when we have two bodies in contact with a normal load P and the tangential force Q that will generate partial slip at the contact interface. And we'll talk about fretting fatigue when we will have PQ and the fatigue stress sigma. And the particularity of fretting and fretting fatigue is the fact that we have a strong stress gradient at the contact edge. We also have stress gradient at the crack tip. And in fracture mechanics, we have tools to take into account this gradient effect. So these tools are intensity factors. For example, in a reference frame attached to the crack tip, the velocity can be explained like that in 2D with K1 the stress intensity factor of mode 1, and K2 the shear stress intensity factor. And in the non-local approach, we just use the same quantity, but to describe what happens near to the contact edge. So, for instance, the equation 1 will be rewritten for contact problem in equation 2. But in equation 2, we will add a new term that we call I2C, psi2C, that take into account the partial slip at the contact interface, because at the crack tip, in this formula, we don't have the partial slip. So for the contact, as we have partial slip, so we'll add this term. And when we will have fatigue, we'll add a term to take into account the fatigue effect. So this is the non-local approach. We just use fracture mechanics quantities to describe what happens close to the contact tip or contact edge. Yeah. Okay, so now I will talk about the lifetime prediction under variable normal loading conditions using our non-local approach. But first, I will start by describing the experimental setup. So this is a actuator machine. So it means that the normal load the fretting force and the fatigue force can be applied independently. For example, the normal force is applied with the normal force actuator that you have here. The fretting force is applied with this actuator, and the fatigue force with this actuator. And so the machine is capable of doing a pure fretting test, fretting fatigue test, variable normal loading condition test, high temperature test, and lubricated condition test also. And the machine is developed at Safran Raffendienst. So it's a specific test bench. And our specimens looks like that. So it's kind of demonstrate. Okay, so for the numerical simulations, so our specimens looks like this. So we model them like that for 3D simulations. So the normal force and the tangential force are applied at the top of the pad, and the fatigue stress is applied at the left of the specimen, and the right of the specimen is fixed. And yeah, for the contact for the friction coefficient, we use 1 because it was determined during a test that the friction coefficient between for let's say our material is 1. So we use this value for the simulation. Okay. Okay. So during the simulation, during the test, sorry, the normal force is time varying. So during the simulation, we also apply a normal force that is time varying. So the normal force is not constant, as you can see in this graph. The red curve is not constant. And when we look at the stresses inside the specimen along the y-axis, we can see that the sigma xx, so in red, fits well with what we can have fits well with what we can have with analytical formulation. It is the same with sigma yy, so in blue. But when we look at the sigma zz, the one out of the plane, we can see that the analytical solution that's in black line, and the numerical solution which is in a dot line, so that doesn't fit correctly. So it means that we are not in plane strain assumption. So yeah, sigma z is not equal to nu sigma xx plus sigma yy. And when we look at the stresses at the contact interface, we can see that we have edge effect because the stress is not uniform. We can see that the stresses at the edges, let's say, are low than the stresses at the center of the contact. Okay, so as I mentioned during the simulation, the normal load is moving, and we know that let's say for this kind of configuration, the normal load dictates where is the contact front position. So it means that if I vary the contact force P, the extent of the contact zone will vary. So it means that let's say if I press a lot, I will have a big contact zone size. If I press less, I will have less contact zone size. And for example, if my normal force vary like that, the figure in the middle, so my contact front position will also vary like that. But to use the non-local approach in equation 6, I need to know where is the contact front position to extract my intensity factors that I need. So for that, we develop a robust contact front detection methodology to track the contact front position with the aim, let's say the methodology that we develop let's say, is general and applicable to a variety of contact problems, and is able to work if the contact configuration is Hertzian or non-Hertzian. And this method, and to detect the contact front detection with the methodology, so we minimize the residue between the displacement field in the region of interest. So the region of interest is this zone in red. So we minimize the residue between the displacement field in the region of interest and its approximation. So it's non-local approximation. So equation 7. So we build a kind of eta function that is the residue. It was the first approach, but if we want to take into account the physics of the problem, we notice that the symmetrical part of the displacement field, so the symmetrical term I1 psi1, dictate the extent of the contact zone. So to detect the contact zone positions, we then minimize the residue on the symmetrical part of the displacement. So we use equation 9 instead of equation 8, which is more stable and give good results. So to validate the methodology that we propose, so we made some test cases with cylinder plane contact configuration, and we noticed that when we apply the methodology, so the minimum of our residue on the displacement field coincide with the theoretical contact front position. So we have we are at 1, so it means that our contact front position is at the theoretical contact front position. And when we apply the methodology to all the time steps, so we obtain this graph when the contact when the contact front is supposed to be fixed. So, and the analytical solution is the horizontal black line, so the Hertzian solution. And we can see that we are able to detect contact front position that are around the analytical contact front position. And when the contact front position is moving, so we are also able to detect the contact front position. So the methodology is general because it is based on the displacement field, and it is also low mesh dependency. And to test the robustness of the strategy, we add random noise to the displacement from finite element simulation. And we see that we are able to detect the same position. For example, the position detected without the noise are in red, and the position detected with noise are in blue. And we can see that the positions are the same, which means that our methodology is robust. So now we know the contact front positions, so we can now extract our intensity factors. And here, so I plot the intensity factors of mode 1 as a function of time and along the specimen thickness. And similar to mode 2, I plot it here. And we can see that we don't have the intensity factors at the edge of the contact are not the same with the intensity factors at the center of the contact. So we have some differences due to the edge effect that we have. And here, when we compare the solution with our algorithm with the contact status algorithm that is in blue, and our algorithm is in red. When we compare the contact status solution, so in blue, the algorithm that we developed in red, and the analytical solution in black, you can see that the solutions are closed. Okay. Now we know the intensity factors, so we can compute damage parameters. The damage parameters were proposed in the thesis of Guilhem Rousseau. So we have a volumetric criterion, which is a non-local version of Archard law. We have the tribological damage parameter, which is a kind of accumulation of partial slip at the contact interface, and we have the dissipated energy criterion. So that is here. But in the case of variable normal loading condition, we noticed that the contact front was moving. So it means that the crack initiation point is moving, and it means that we have a kind of spatial dispersion of contact damage. And to take into account the spatial dispersion of contact damage, so we add the function f of x, which looks like this, to take into account the spatial dispersion of the damage. And when we plot the criteria, the tribological criteria, we obtain this, and this shows the damage of the contact surface. And when we zoom in this zone, in this red box, we can see that all the three criteria are not the same, in the sense that they do not distribute the damage in the same way. Okay, so so we compute non-local damage parameters. We can use them to predict lifetimes. And to do so, we take experimental values of tests. And so for each series of tests, so three tests were done in the same conditions. And to predict the lifetime, so I use the mean values of each series that you can have here. And I also plot the uncertainty that you have in black horizontal line. Okay, so by using the non-local crack initiation criteria, I can predict the lifetimes by using, let's say, the volumetric criterion CV, the dissipated energy criterion CED, and the tribological criterion in black, so CTD. So I can predict and I can compare to the lifetime that we obtained from experimental tests. And we can see that when we look at the gaps between the real value and the predicted values, we can see that we are below the uncertainty of experimental data. And when we plot the predicted lifetime, again, let's as a function of the experimental lifetime, many points that were predicted are below the first B sector, which means that most of the predictions are conservative. And I will finish by saying that, okay, so in this for this talk, so we propose a new contact front detection methodology to track the contact front position, and the methodology was applied to detect the contact front position during 3D simulations. And we also predict a fretting fatigue lifetime under variable normal loading conditions, and we obtain good predictions between experimental data and predicted values. So thank you for your attention.